Let's try and prove this statement true by using proof by mathematical induction. This is actually a sum that we're trying to prove, but it's very difficult to see while it's still left in sigma notation. So the very first thing that you always need to do when you get this is to expand the left-hand side. Now you'll remember that the number at the bottom is your first substitution in the place of I, and the number at the top is your last substitution in the place of I. And the numbers go up consecutively from the number 1, i.e. the number at the bottom. If I substitute 1 into I get 1 squared, which is 1. Then if I substitute in 2, I get 2 squared, which is 4. Then 3 squared, which is 9. And so I go on until the very last number, in which I substitute an n in the place of I, and I'm going to get n squared. In other words, what I'm trying to find is, if I take 1 plus 4 plus 9, and then all the way up to n squared, could I get that answer if I had used the formula of n plus 1, 2n plus 1, all divided by 6? We're going to start by testing it first of all for n is equal to 1. If I want to prove the statement true for n is equal to 1, I need to do it first on the left-hand side. On the left-hand side, I'm going to get 1 squared, and that answer is 1. On the right-hand side, if I replace every single n with a 1, I'm going to get 1, and then 1 plus 1, and then 2 times by 1 plus 1, all divided by 6. Work this one out and see what the answer is going to be. If you worked it out, you would have got 3 times 2 times 1, which is 6, divided by 6, and that answer is also 1. In other words, we have proven that the left-hand side is equal to the right-hand side when n is equal to 1, which means that the statement is true for n is equal to 1. In the first part of our assumption, which is the first part of induction, I must prove that the statement is true for n is equal to k. Do you remember what we did before? All we did was we took the n's and we replaced them with a k. In other words, I'm going to assume that 1 plus 4 plus 9 all the way up to k squared is going to be found by taking k, timesing it by k plus 1, by 2k plus 1, and dividing it by 6. Now we've finished the first part of our induction. We now need to do the proof part, which is proving it true when n is equal to k plus 1. Like we did in example 1, I need to understand what I'm trying to prove. So I need to prove the following. Remember, when you're proving, you are going to take the k and you're going to replace it with k plus 1. In other words, I want to find that if I take 1 plus 4 plus 9 all the way up, I am going to find up to k plus 1 squared. And I want to prove that that could have been found if I took k plus 1, remember I'm replacing k with k plus 1. Then I've got in the first bracket k, which is now k plus 1, plus 1. So that's going to be k plus 2. And then in my next bracket, I've got 2 times k plus 1 and plus 1. And all of that must be divided by 6. Remember, when we do this step, we must start with the left-hand side and try and prove it equal to the right-hand side. Starting with the left-hand side, I am first of all going to take a look at what information I can take from my assumption. Now, do you remember that in your assumption, this part of the statement looks exactly like this part of my statement in the proof? In other words, I'm going to replace that in my proof by this statement over here. So I can now write my left-hand side as k plus 1, 2k plus 1 all divided by 6, and then plus the additional term of k plus 1 squared. Remember, I can't write the right-hand side down because I'm proving. As the right-hand side had a common denominator of 6, that is going to be my next step. So in my next step, I'm going to write all of these numbers over a denominator of 6. The first term already had a denominator of 6, so that remains unchanged. The second term needed to be times by 6. And now I need to simplify the expression that I've got so that it can look like the right-hand side of my proof. I want to get a bracket, which is k plus 1. I want a second bracket of k plus 2. The third bracket that I want is going to be 2k plus 3, and that must all be written over 6. Can you spot that I can already get my k plus 1 bracket because there is a common factor of k plus 1 in both of those terms in my numerator? So I'm going to take out that common factor, which means that I'm left with k all times by 2k plus 1, and then added to 6 and k plus 1 from the second term, divided by 6. Now I don't want to disrupt that k plus 1 bracket, so now I'm just going to work in that second bracket. So now I have k plus 1. In the second bracket, I've got 2k squared plus k plus another 6k, which is 7k, and then I've got plus 6. This second bracket can now be factorized further using the trinomial method. And when I factorize it, I'm going to get that the two bracket factors that I get are going to be k plus 2 and then the bracket of 2k plus 3. This is exactly what I was looking for. In other words, I have proven that the statement is true for n is equal to k plus 1. Remember to write up your conclusion. And then always write up the full conclusion for the proof that you did using mathematical induction.